Hi all. So today I actually want to talk to you about organizing some of the information that we've done in our most recent chapter. So this is Solomon chapter, I'm redoing this. That should be Solomon chapter 17, and then it's Klein book chapter 18 and 19. And this is all about this is when ketones attack. That's what I'm going to call it. When ketones attack. So we've learned a lot about what happens when ketones get attacked or when carbonyls get attacked, but we have not talked at all about them being able to act as a nucleophile. So that's what this chapter is all about. And a lot of my students have told me that they're struggling to maybe synthesize is a good word, this information, like bring it all together and kind of know what's going on. Like some of the students who, usually don't struggle with that as much have reached out to me to share about that. And so that makes me think maybe it'd be worthwhile to kind of organize some of this information for you. So that's kind of my goal for right now, is to help organize this information. So here's what I think are some of the big takeaways from this chapter. So one is you need to know what keto-enol tautomerization is, and then you also need to know how enolates form. You need to know what base to choose, because it's basically just an acid-base reaction. And then you also need to know thermodynamic and kinetic product if it's not symmetrical. And then for reactions of these, so that's how to make the ketone be able to attack. And then when it does attack, it can do a few things. One is called alpha halogenation, which basically means you make your enol, this is the alpha position, and then you put a halogen right there, okay? And you can do that in acidic, basic, and there's a special one like HVZ, hell something, I don't remember. But it's basically PBr3 and then bromine to do a bromination. So those are kind of the three ways you can halogenate. Once you've halogenated, two more things can happen. That's a haloform reaction or an elimination reaction. Okay, so that's one class of reactions, is alpha halogenation. You can make it happen three different ways. And then once you've halogenated, oftentimes you'll see a further reaction. And we'll go through these individually, but I'm trying to give you a big overview of this chapter. Then the next big reaction that we have is alpha alkylation. So that's basically the same thing. You make your enol, and then you basically just do an SN2 reaction, and then you have an R group there instead of whatever, this being a nucleophile, it'll do a substitution reaction. So usually you react it with RX. And so this would attack, and the leaving group would leave, and you'd have this. So it's just an SN2 reaction. So, and actually alpha halogenation is also kind of an SN2 reaction, because you just have a bromine, and the nucleophile attacks and kicks out the other bromine. So you basically are just getting two SN2 reactions, but just kind of specific ways to make those happen. And then there are some condensation reactions. So that's Aldol condensation and Claisen condensation. And these two are basically exactly the same, except that Aldol condensation happens with not esters, and Claisen condensation is more ester focused, but their mechanism is very, very similar. And there's a few exceptions with Claisen that we can get into, but this is overall what you need to know for this chapter. We did talk about, but this won't be on the exam, Michael additions and the stoichionamine synthesis. That is game for your final exam. It may be on the ACS exam, but it's not probably going to be on your on this upcoming exam. These things are all fair game for your upcoming exam. So hopefully this kind of helps you know what you're looking for. Know what you need to know. You need to know how to make a ketone be able to attack. So that there is a keto-enol tautomer, and that kind of relates to when you apply a base to this keto-enol tautomer, you get enolates. Enolates are what enables ketones to attack. And when ketones can attack, they'll do SN2 reactions to make halogenations or alkylations, or they'll attack other ketones to do additions and ultimately condensation. So like that's it. That's everything. But we're going to zoom in on each of these individual parts first. So, or not first, we're going to do that now, but I wanted to go over all of that first. So the first thing was keto-enol tautomerization. So all that is basically, it's something between resonance and maybe like a methyl shift. It's basically, or maybe they're more like isomers, tautomers, maybe more like isomers. These are exactly the same in terms of their makeup of carbons, hydrogens, oxygens. They can be in either form. You can go from the ketone to the enol with acid catalyzed conditions, or I think base catalyzed conditions. So if you have a ketone in the presence of a positive charge, it'll protonate it, or have a proton, it'll protonate it. And then usually that's attached to OH2. So if you take this proton and then you have water left behind, and that water will steal this proton, come here, oh, that should be an H, and kick up, and you get OH and this double bond. So that's basically an acid catalyzed keto-enol tautomerization. And the reason they're called keto-enol is ketone, keto, and then enol, there's a double bond, so ene, and an alcohol, so all, so enol. So that's how you get these names, keto and enol. So that's all that is. And I feel like that isn't as important in this chapter as enolates. So let's talk about enolates, which is when you apply a base to a ketone. So if you have a ketone, the ketone is usually favored also unless there's a specific reason. I guess I should say that. So like when you have two ketones together, a lot of times it will actually, the second one will favor the enol position because there's some hydrogen bonding available. So usually the ketone is favored, but like in this case, this one favors the enol. Or if you had this structure, if it went into the enol position, that would be a phenol, right? So this actually is the more stable version. You've seen phenol, you've never seen a ketone like this because it can form aromaticity. So unless there's a good reason for it to be in the enol form, it prefers the ketone form. So that's why I think this kind of like isn't as important as what we're going to talk about next, which is making the enolate. So if you have a base with your ketone, these hydrogens right here have a pKa of about 20. And if you steal that, this can come here and kick up, and this forms your enolate. O minus, and you have a negative charge here, or a double bond here, and a negative charge up top. But of course, this can partake in resonance, or this comes down and kicks out, and so then you get this structure. Now, either of these, I'm going to redraw without the arrows, either this oxygen or this carbon in theory can attack. But I'm going to talk about which one does attack, and I'm going to use conjugate acids and conjugate bases to kind of talk about that. So if you protonated this and you had its conjugate acid, it would be an alcohol, and those have a pKa of 16 to 18. If you protonated this, it would be an sp3 hybridized carbon right here. And you know now that that has a pKa of about 20. So the pKa of this is a weaker acid than this. So if this is a weaker acid, then that means the weaker acid is a stronger base, right? So if we know that, then we know that between these two, this one is a stronger base, so this one is going to be a better thing to attack. So usually the carbon position in the enolate undergoes, is the one that's going to attack. So sometimes people will draw, I don't know why people do this. Oh, I forgot. There's a double bond right there. and right here. I don't know why people do this, but sometimes they'll draw the attack happening like from the negative charge being on the oxygen. So like if you're trying to attack, like, let's just say H+, they'll draw this coming down and this attacking. I personally don't like that. I think this is much more clear and it's less arrows. So I just draw that usually. These both mean the same thing because they're both different resonance forms. But yeah, I just prefer to draw the attack always from the lone pair on the carbon. So you won't see me do the enolate form in the O- resonance structure very much. I will usually do the enolate in the carbon minus structure more often. So I just kind of wanted to touch on that. And then the other thing is if you have an asymmetrical ketone, there's going to be two different products you could get. You could either get this enolate or you could get this enolate, right? Both of these have negative charges on them. Either one of these you could get. One is thermodynamic and one is kinetic. So the thermodynamic is the one that's more stable. So this is actually the thermodynamic one, the more substituted side. Because if you think about the double bond that's there, this one, a more substituted double bond is more stable than over here. Oh, this should be L minus, sorry. If you had a double bond there, that would be less stable. So this is the thermodynamic one, and this is the kinetic one. Kinetic is usually favored in lower temps, and thermodynamic is usually favored in higher temps. Okay, so where are we at on our list? We've talked about what keto-enols are. We've talked about what enolates are. We've talked about thermodynamic and kinetic product. I haven't talked much about the base. So this is basically just an acid-base problem, right? So the acid plus the base would equal your conjugate acid and your conjugate base. So this is the conjugate base. And then you'll have your conjugate acid, which is like BH, your conjugate acid. So this is the original acid, pKa of about 20 right here on the alpha hydrogens. Because the reason it's 20 is because of the resonance stabilization. We'll talk about that in the group work today, but basically because there's resonance to stabilize that lone pair, it's more willing to give up its proton. But basically you have this. And so depending on what your base is and what your pKa of your conjugate acid, that could favor one side or the other. So this goes all the way back to like chapter 3 when we did acid-base reactions. But if you have ethoxide, for example, plus your ketone, that forms your enolate plus alcohol. And then you can compare the pKa of this acid is 20, and this alcohol is probably somewhere from 16 to 18, right? Just to estimate, alcohols are usually somewhere from 16 to 18. So this alcohol is a stronger acid than this. So the weaker acid is usually favored. So this side would be favored. So this wouldn't be a very good reaction. But then another option that we have is LDA is used a lot. That's, let's see, lithium, so it's Li+, but the amine has 2 negative charges. So lithium diisopropyl amine, that's where LDA comes from. The L is for the lithium. The D is for diisopropyl. So these two isopropyl groups, and then A is amine right there. So if you have this reaction, you end up with your enolate plus a protonated LDA. And a protonated LDA has a pK of like 36 or 38. It's somewhere in the 30s, and this one's 20. So we want the weaker acid to be favored. This is the weaker acid, so then our enolate will be formed. So you really basically need to pick a base whose conjugate acid is bigger than 20 if you want to favor this side. Now, one thing that I do want to point out, so that's just the basics of keto-enol. When you have two ketones, this pK is like closer to 9 or 10. So you actually can use ethoxide for that, O-. Ignore that scribble, because the thing you get is a pK of like 10 compared to a pK of 15, or I guess 16 to 18. So this side is actually favored. So you have to really consider the pKa of the thing you're trying to deprotonate and the base that you're using, the conjugate acid of that base, to decide which side of the reaction it's going to favor. And in general, you need a base whose conjugate acid is going to be a larger pKa than whatever you're trying to deprotonate. So in the case of ketones, it needs to be bigger than 20, so like 36. In the case of diketones, it needs to be bigger than 10, so like ethoxide would be great. Okay, so that is an overview of what a keto-enol is. Check. We talked about what enolates are. We talked about how to choose a base. We talked about thermodynamic versus kinetic products. So now let's talk about halogenation. So for halogenation, alpha halogenation, you can do this 3 ways. You can do this in basic conditions. And essentially, that would mean you have your alpha proton, and then you have OH minus, and then Br. This is probably going to be less effective because of what we just talked about. This isn't as strong as like LDA, but you can do it with this. This will come here, kick up, and you get your enolate. But again, I actually usually draw my attack from this position. So this is going to attack your Br and break that bond, and then you get an alpha halogenation. Oh, I drew that wrong. It attacks right there, so it's one away. So it's bonded to the alpha. So you get your alpha halogenation. The thing about it being in basic conditions is actually a lot of times it will keep going. So it'll give you 2 and then react again by the same mechanism and give you 3 bromines. And that's kind of a lot. These are very withdrawing groups, right? So that makes this carbon center pretty nucleophilic. And so actually the OH minus can come and add in because that center is so nucleophilic, and you'll end up with something like this. And then this can come down, and this, because it's so electrophilic there, this can leave as a good leaving group, and you get a carboxylic acid plus CBr3 minus, and then usually this will become acidified and it'd be CHBr3, basically. So this first alpha halogenation is just a basic base catalyzed alpha halogenation, but it keeps going to form this. This is called bromoform. And overall, this is known as a haloform reaction because it works also to make CH3I, and one that you've probably heard a lot, chloroform. So there's bromoform, chloroform, and iodoform, and all of these are CH and then 3 halogens, and they can all be formed by adding sodium hydroxide plus that halogen to your ketone, and it will react over and over to get you a haloform. So that's a base catalyzed alpha halogenation and also a haloform reaction. Acid catalyzed, I'll use a different ketone this time just for fun, will come and attack, and you'll get, usually if you have a ketone in acidic conditions, it'll get protonated first and then something will attack. Or if not, if you have a ketone in basic conditions, usually the attack will happen first. So that's what we saw here when the base deprotonated first, the attack happened first. Okay, so after we get our protonated situation, the next thing that usually happens when you're going to try to do something at the alpha position is you form an enolate. And in this case, because this is protonated, the electrons are being pulled up away from here, so this hydrogen is going to be even more acidic than normal. So this is going to come in and take this proton. Just water is all the base that you need because it's protonated there, and you'll get OH with a negative right here. And this bond broke here, so actually this is positive. You can also draw it as OH with a double bond there. Okay, so the thing that we've seen over and over is the negatively charged right here attacks. In this case, drawing it attacking from there doesn't make as much sense as drawing the double bond from the attack. That's why I kind of drew both of them for you. I do favor the other one, but if you have a positive charge next to it, it doesn't make sense. So this comes back down, and then this double bond attacks the bromine, and this breaks, and you get your alpha halogenation. OH, Br, this came back down, so this is positive. And then the Br minus in solution or whatever else will come and deprotonate that, and you'll end up with your halogenated ketone. So now you have, you've seen a base catalyzed halogenation and an acid catalyzed halogenation. And then the very last one is actually a special case. It's if you have a carboxylic acid and you want to halogenate at the alpha position on the other side. You have to do something with this before you can do anything over here. So actually people typically use PBr3 to turn this into a bromine, and then you use Br2, and that will halogenate at the alpha position. And then people will use water to bring that back to a carboxylic acid. So this is called, I can never remember, it's like HVZ, but this is a way to do halogenation at the alpha position when you have a carboxylic acid, and then to get the carboxylic acid back after you've halogenated. So what have we covered from our list now? We've done alpha halogenation, we did basic, acidic, and PBr, and we also talked about haloform formation. We didn't do elimination, so let's go ahead and do an elimination one. So I had used, I'll just do it again just so you can see. I used H plus, H3O plus actually, H3O plus, and Br2. And the first thing that happened is that protonated, and then you get a protonated ketone and water, and then this protonated ketone is going to get deprotonated by water. That should only have one lone pair. So a hydrogen here will come take this, go here, and kick up, and you get OH, plus you've got a double bond here, and then you have your Br2. So this will come down, this attacks, and this bond breaks, and you get a protonated ketone. People will deprotonate it with water or bromine or whatever else, and it's got your bromine at the alpha position. So let's deprotonate it with we'll just use water, put it back in water, and then you have your halogenated alpha halogenated ketone. But the thing is, there's a hydrogen available right here that you can undergo just a classic E2 reaction. So if you use a strong base like pyridine or even ethoxide, tert butoxide, so let's use tert butoxide to favor elimination and heat. This will come and attack this hydrogen, leaving these electrons behind, and the bromine will leave. And you'll get, this is known as an alpha beta unsaturated ketone, but basically you've just formed a double bond. So this isn't a new reaction at all. It's just kind of like what's new about this is you made the alkyl halide. So you made the alkyl halide, and then you can use pyridine, you can use tert butoxide, you can use anything to take this hydrogen away, and it will do an E2 reaction basically. And you've seen E2 reactions over and over again. You're just seeing it in a new context now. So that's the elimination reaction. So that's all about alpha halogenation. Now, alpha alkylation is actually even more simple, I think, than alpha halogenation, because this is definitely something you've seen before. You basically just need to have your ketone, react it with a good base to make your enolate, like LDA is a good base to make enolate, right? We talked about choosing your base. And that will make your enolate. If you want to draw it, all the way up, or this comes here and this goes up, you can draw like that too, O minus. Either one of those is okay as long as you know that you're attacking from this position right here, because that's the part where the conjugate acid has the lower pKa, so it's a weaker acid, so that part is a stronger base, just like we talked about earlier. And then you're just going to have any old SN2, anything. So you can come attack here and kick this out, and you will get an alkyl group at the alpha position. That's literally it. This is actually just an SN2 reaction. And you're making the nucleophile by using a base to create the enolate, and then it's just doing SN2. So if you see a ketone with LDA followed by anything with a halogen, other than just a halogenation reaction, you're very likely to, with an alkyl halide, get a substitution reaction, and it's just going to alkylate at that alpha position. So something like this. So that's literally it. So LDA at colder temperatures will favor, if you have an unsubstituted, the more substituted thermodynamic side. Unsymmetrical. So if you have something like this, LDA at cooler temperatures, like below room temperature, will favor the kinetic product. So it would actually favor alkylation like on this side. If you can use NaH and heat, and you can favor, it starts to get risky because then you start to also have elimination start to be an issue. I guess you wouldn't have elimination because you'd have elimination be an issue with your with this like an interfering reaction would be elimination on your alkyl halide. So you don't want to use too much heat, but like room temperature slightly above with NaH will favor the thermodynamic, more stable, more substituted side. Okay, so that's alpha alkylation. That's it for this chapter, or for that chunk of this chapter. And then let's get into condensation reactions. Condensation reactions, again, are about ketones attacking. And usually they're going to attack themselves. So aldol condensation is if you have you have a ketone and you add a base to it. And let's just have it attack itself. Actually, I don't want it to be in the same color. I'm going to do a fancy schmancy situation where we let it attack something with a different color. Okay, so these electrons are going to come over here and form a bond, and those will get kicked up. So you'll have, so we have our hydrogen, carbon 1, carbon 2, carbon 1, carbon 2. The electrons form a bond between carbon 2 and this carbon right here, which we're calling carbon 3. So this bond came from these electrons. This bond was already here, and then you have your minus right here. There's a methyl group present on the thing that was attacked, and there's also a hydrogen. You don't have to draw the hydrogen, it's implied. So probably if you didn't have the hydrogen implied in there, it would look like this. And then depending on what you use to make the base in here, this will be protonated. And you'll have, I should have done this. This will be protonated, and you'll get aldol addition. However, aldol addition is not very stable. Aldol addition products are usually not very stable. So actually what will typically happen is there's a number of different ways people talk about this happening, but basically either you have O- in solution from a water that got deprotonated or who knows what. This will come here and this will kick out. I don't like drawing it like this because I don't think OH is a good leaving group. So actually I usually draw it like this. This is more confusing to you. That's fine. I don't want to confuse y'all. But I basically have this alcohol comes still, this pretty acidic proton, and then this kicks up, and then this leaves kind of all in one step. So it's kind of sneaky of me, but basically this adds the hydrogen from down here, then this is a lone pair, it'll go here and leave. So, after it first stole the hydrogen, it would look something like this, OH2 plus, and then this is a lone pair here, and then the lone pair will come and kick up. It very likely happens all in one step. Like that. So basically, this is just, all this is an acid catalyzed dehydration if there's acid present, or just a dehydration. But basically, you're losing a hydrogen from here and you're losing water from there. And this is the condensation. So the first part is aldol addition, where you have a ketone and an alcohol. And it can form to some degree because this hydrogen will be stabilized by what's that called? Hydrogen bonding right here between this oxygen and this hydrogen, but it's really not the happiest. So the water will leave, and the condensation product is favored, especially when heat is present, or if you let the reaction go for a long time. Let's see. Do I have any other thoughts on this? Let me check my notes. I don't think I do have any other thoughts. Okay, that's kind of the main thing. You can get what's called a crossed aldol condensation, and that's just when the R groups are different. So like if you have an R group here versus a different R group, we'll call R prime over here. That can be when it gets tricky, because this can react with itself, or this can react with itself, or they can react with each other, and either one can be the attacking group. So, but it's still just an aldol condensation. The mechanism is the same, but it's just like if you have, let's say, this enolate and this one, we'll do this. So you could have this attack on here, and you get O minus. And you'd have a methyl here, and then this. And then it would be OH after it got protonated. And then this leaving group could get kicked out, and you could have the double bond right there. Or you could have this attack itself, which is basically what we had drawn up there. So it would look like this. Or you could have this attack itself. So that would be harder to draw without actually going through the mechanism for me, but OH, and then there'd be this branch chain and a methyl. Or you could have this side be the attacker, so OH and a methyl. There's a hydrogen right here. So these are all the possible things you could get. But this is just a crossed aldol condensation, because it's two different things attacking. These are not really effective unless you do a crossed aldol condensation that only has one good alpha hydrogen to take. So I'm going to do the first step of the reactions that I usually did was benzaldehyde and acetophenone. So this is a real reaction that I did in my research lab. Every single day, I literally would go in and do this very often. And so you'd form your enolate with KOH, actually would be the thing that we would use. Oh, I wish I had drawn this in a different color. So I'll make this one pink. So this comes in attacks. So this one's all pink. And these electrons right here form a bond. And you get your OH minus, or your O minus, but it gets protonated to become OH. We would do an acidic workup, but actually we would let it go long enough to where this leaving group would leave, and you would get your condensation product. Okay, so technically that's a cross-aldol reaction, but there's only one good alpha hydrogen because these are attached on benzene rings, so there's no hydrogen right there where it's substituted. So there's only one alpha hydrogen, so only one product can possibly form. So this is a better design crossed aldol condensation than this, but technically they're both the same reaction. So that's the basics of aldol condensation. Claisen condensation is basically the same exact thing, but it's just with esters. So Claisen condensation, there is one thing that's different, and that's that you have to make sure you have to have at least 2 hydrogens here. So you can only have 1 methyl. And you'll see why. I can talk about why at the end. You can only have 1 R group. You can't have 2 R groups, which we have done with an aldol condensation. And I'll talk about why at the end. But basically, Claisen condensation is the same thing. You have an ester and you turn it into an enolate. And I would say there's one other thing that makes these kind of different is that really the preferred base to use is like whatever methoxy you have, or whatever, I guess alkoxy over here, or LDA, but you can't use OH because if you remember, an OH plus an ester will hydrolyze it back to carboxylic acid. So you can't use OH ever. And it's really basically beneficial to use this because if it does try to attack into a substitution, you'll just get the same thing that you already have. So like, if this was an ethyl, we'd use ethoxide, or if that's methyl, you use methoxide. Just, that's kind of the typical standard so that you don't get crossed products. But this comes and takes this and then comes up here and kicks up, as always, to make your enolate. And you can have an R group here or not. But I, of course, like to draw my enolates like this. So that's going to be the thing that attacks, and it's just going to attack the same ester. Let's draw it in a different color so that it's easy to see. It goes down exactly like an aldol condensation. Like the whole thing is exactly the same, where it attacks here and kicks up, and then you get your O with your R down here, and this is the thing where the bond forms. So the lone pair from here, those 2 electrons, make this bond to this carbon right here, O minus. That has a methyl group on it, and it also has an ester. So kind of the tricky thing about this is instead of the alcohol leaving, because it is an ester and that's actually a good leaving group, this can recover and kick out the ester, which you have seen before. So that is the thing that sets it apart. Let's put an R group there, sorry. And then that methyl group is what's left. Okay, so we have an R group, and then we have another hydrogen that's been here in the middle all along, right? This hydrogen. And this actually isn't super favored, right? Because of what we talked about with choosing our base. So if this, the pKa of this conjugate acid of alcohol, when it deprotonated that thing, is like 16 to 18. The pKa of this ester is only what, like around 20? So that's not great. But this being able to be deprotonated, this now we talked about has a pK of closer to 10 because it's between 2 ketones. So the thing that really drives this reaction forward is that you still have ethoxide in solution, and it will come and take this hydrogen, deprotonate that hydrogen, and that reaction is favored because you have this negative is so stabilized that actually this is more stable. The pK of this is 10, and the pK of your conjugate acid, the alcohol, is HO, is 16. So this side is more favored, and so even though this isn't favored, this is favored here at the end. So that's really important that there's 2 protons here at the beginning. You can't have 2 substitutions. You have to have 2 hydrogens for a Claisen condensation to work. So Claisen condensation works almost exactly like Aldol condensation. It does the same thing where it attacks, it adds, but instead of losing a water, you're basically losing an alcohol. And then this alcohol, this ethoxide, comes down, steals this proton, and you end up with this, and you have to add acid to get it all back to neutral in the end. So you would add acid eventually, and that would go back to this form right here. So that's a Claisen condensation. But the initial attack and the addition part of the 2 is the exact same thing. The thing that changes is what is eliminated, because you have a good leaving group here and you don't have a good leaving group in an aldol reaction. So that's aldol and Claisen. So, and be sure with Claisen you don't use OH, and it's really best to use whatever ester you have there. So aldols is for aldehydes and ketones. Claisen is for esters. There's a little bit more to these reactions if you want to flip through your notes and make sure you understand all of it. This is a good overview of what you're going to need for your exam tomorrow, and what you'll need to know up to like Michael additions and Stork enamine and stuff. This is a good overview of what happens, how ketones can attack, and what reactions ketones do when they do attack. So I just kind of wanted to give you all that overview. I hope that was helpful, and I'll be posting the video with the group work solutions shortly.